Sorry, last technical details. Welcome to the NeuroTwin workshop, and thank you for your willingness to participate, not only as public, but also big thanks on behalf of the NeuroTwin team for the invited speakers here today. And well, we have a compact agenda, so I left Giulio to start. Thank you, Giulio.
Thank you, Christina. Yeah, so good morning, everybody. I hope I can make this thing work as usual. It's a pleasure to be here. We have a very interesting set of presentations. I would like to tell you a little bit about what we do in Neuroelectrics and also what it relates to with the NeuroTwin project. So it's going to be a hybrid talk, a hybrid being a word here. So let me just start because I have quite a few things to say. Okay. There we go. I don't know why it doesn't. Okay, so the motivation for this meeting and the motivation for the company that I'm representing here today is really about patients. So we are really committed to developing solutions. So there are many patients in neuropsychiatry that right now don't have solutions for the problems, and we in Neuroelectrics and in NeuroTwin are trying to develop improved solutions based on brain stimulation and more concretely model-driven brain stimulation, personalized computational brain therapy, as I call it here. We use a technology called tES that it's now, I think it's becoming more mature, something that was actually reinvented for better by Michael Leach, who is here with us today, and he will give a talk a bit later. It's a non-invasive neuromodulatory technique, sub-threshold. It cannot initiate action potentials through the application of persistent, mesoscale, weak electric fields at low frequencies. So these are all important words in tES, and we have a technology now that is capable of delivering these currents in a very controlled manner over the head. These are typically small currents, less than 2 milliamperes normally, and they can generate fairly uniform electric fields at the mesoscale in the brain that are capable of altering memory potential of cells, mostly pyramidal, as we understand, and these lead to plastic effects. And typically, this is something that's used for long times, 20 to 60 minutes of application, and it's used with TDCS, which is direct current, and also alternating current of low frequencies is another technique. There are other ones like TRNS, random noise stimulation, that's also used. It's known to be very safe in terms of the power delivered. It's really a small amount of energy that's being delivered to the tissues, and there are no side effects to worry about. When I prepared this slide a long time ago, and I'm not sure it's fine anymore, but I tried to make a simile about what weak, coherent, persistent effects can do on networks. And so here's an example of a network of people that could represent neurons, but also in social terms, it's something that we could do. And if you have a weak but persistent, coherent effect on the network, giving the same message to everybody somehow, you can end up with concurrent effects, large concurrent effects, and plastic effects as well. Okay, so this is a little bit the story. I prepared this slide when Trump was elected, but now there are other scenes that one could make. So just a word about technology. So multi-channel brain stimulation. So up to 32 electrodes that can deliver controlled currents independently in each electrode, as long as we conserve current, of course. And this can be designed in many different ways. Part of the complexity is precisely this aspect that it can be configured in many different ways. And so it's a powerful technique. It's complex, like the brain is complex. So a key question I would like to move in front of the camera is how to optimize it. And I think part of the rationale is to develop a good model of what it's doing, and that's what it's all about in terms of the NeuroTwin project as well. So let me tell you a bit about the NeuroTwin project, which is a project that it's been spearheaded from Neuroelectrics with this idea in mind, and it's a project that started a year ago now. It's a 4-year FED project with the Commission, and basically, the idea is to work on AD. So try to develop improved protocols for AD patients with this idea of model-driven brain stimulation. So the vision of the project is that the human brain is a dynamical network, and for neuropsychiatric disorders therapy with tES and with other ones, I think, entails rewiring of this network through plastic mechanisms. The vision is also that each brain is different. We need to understand how different it is to better define this, but it's clear that everyone has their own different problems and different anatomies. That computational modeling is going to be key to improvement of this therapy. So NeuroTwin really means personalized, realistic brain models as needed for the application of the therapy. So that's the goal. For your project, as I mentioned, there are 7 partners. They're all present here, pretty much, almost everybody. And you will see some of the faces in the project here. So all these people are basically here in the room, and I hope you find a good chance to interact with them. We're very excited to work together. It's a very fun team. And I think now that we're over a bit the COVID phase, we're happy to interact physically as well. There's another project that is ongoing too, which is called Galvani, and it's related to NeuroTwin, and it's the other part that we're doing. At Neuroelectrics, it's an ERC synergy project, and the idea is to control epileptic brain networks through brain stimulation via computational models as well. So it's very related, and these are my co-PIs, Fabrice Wendling and Fabrice Bartolome, and it's a real pleasure to work with them as well. So what is a NeuroTwin? I wanted to say a word or two about this, especially in light of discussions of the philosophy of NeuroTwins and also communication to the wider public. So a NeuroTwin is a personalized model. That's the first thing to say. More precisely, a model of a brain, of a head, and of a patient, of a specific patient, okay? More precisely, it's a compressed computational rendition of reality fit for purpose. So there's a purpose for what we do. It's not just a NeuroTwin for the sake of copying somebody's brain or anything like that. And the purpose is to optimize the brain stimulation protocol. So that's what we're doing in both in NeuroTwin and in Galvani, to develop these models for optimization of brain stimulation in the context of a specific pathology. So in NeuroTwin, this is Alzheimer's, in Galvani, it's epilepsy. And lastly, it's in the context of a specific patient as well, of course. And in the projects, we are considering all these elements at the multi-scale and at different levels of abstraction. And I want to tell you what I mean by that. So here's a picture of the 2x2 matrix where you have different scales at which one can study the problem of computational brain models, and also at different levels of abstraction. So this would be the most abstract level, would be like an Ising model, which I will briefly mention, in which you basically assign 1 state to each parcel of the brain you need to work with. Hoff models that can represent oscillations. And then we have level of more detail, still pretty simple compared to what the actual brain is, which are neuromass models, in which you try to represent the activity of populations of neurons connected through networks. And in all the above, as needed, we can also combine the physics part of the problem, which is very important in brain stimulation, because we're dealing with electrical currents, electrical fields, and real heads. So this is the structure, the conceptual structure of how we work on the projects. So what do we need for tES optimization? We need realistic physical models of the electric field in the brain. That's kind of a given. And appropriate models of physiology for the representation of the pathophysiology or physiopathology of the particular disease. We need a model of the electric field interaction with the neuron on the neural populations. Plasticity models of some sort, because as I mentioned, what we try to do is wire brains in a sense. And of course, we need a definition of healthy state. When we start from a pathological one, we want to define what a healthy state and what does that mean in terms of the model, so we can drive through brain stimulation the state of the patient from unhealthy to healthy somehow. Okay, so now I'm going to talk a little bit about the physics part, and then I will talk a bit about the physiology, and that will be basically the time. This has been developed partly in the context of two earlier FED projects, so the project Hive and Luminous, where Hive was the one that we basically started working with stimulation, and Luminous we kept developing, especially the physical brain modeling part. So tES physiology and basic mechanisms of action. The primary mechanism that we understand is the alteration of the membrane potential through the application of these electric fields. These are weak uniform electric fields, and those are the concurrent effects, the ones that happen when you apply the electric field, and then you have plastic effects that outlast the stimulation are the ones that we want to actually rely on. In vitro and animal studies have shown repeatedly that you can change the membrane potential of especially pyramidal cells because they're elongated, so they couple more strongly with the electric field, and this leads to changes in firing rate, in timing of firing, etc. And just to give you a flavor of how that works, so when you apply an electric field like this, you can imagine that there are ions inside the cell that are captured by the membrane. And when you apply the electric field, basically, let's see if it works. Yeah, it works. So almost works. Okay, good. So you have this polarization effect in which ions displace inside, and this is the physical mechanism by which the membrane becomes polarized as well. In this case, we tend to look at the soma as being the main player in these cells. We have simple models for the time being, and in this case, we have a polarization of the soma, and the field will be excitatory in the opposite direction. You can imagine that it's going to be the opposite, basically. We have mathematized this, the first mathematical representation of this for modeling purposes. It's called the lambda E model, in which you assign a dipole to the cell, and then you compute. You present the membrane alteration to the dot product of the electric field and the main direction of the cell and the space constant. So it's a simple model, and at the end it boils down to saying what matters is the component of electric field that is parallel to the cell. So the tangential one we discard in many applications right now. One of the surprising things that I still like to understand better is the sensitivity of populations of neurons to electric fields. This has been known for a long time. If you're interested in this, we have a paper that describes effective interaction in the brain, trying to model electric fields generated by the brain. But there's a nice review of in vivo and in vitro studies of this very surprising, sensitive to weak electric fields by populations that you would not necessarily expect from the alteration of a single membrane, which is very tiny from the electric fields originally. So this is something that we would like to understand better, but it happens, and therefore we need to model electric fields. And for this reason, we started work actually that preceded with Pedro Miranda. We have collaborated quite a bit in the development of finite element models. So this is an application of engineering techniques using other fields to represent electric fields in the brain with accuracy by solving the partial differential equations that matter. Starting from realistic, from MRI of each patient, we can construct these finite element models that represent electric fields with the detail that we need. And this is something that's pretty mature now, and we have operational pipelines in the company that use this. Here's an example of the electric fields that you can obtain from tES, TMS, which is transcranial magnetic stimulation at the rate of 2. This is electrocomposite therapy. And what I want to point out here is that you have different types of electrodes, which are rarely seen, but the coils and the large electrosporicity. But what's interesting to note is that, again, that electric fields are very weak. If you look at the scale, these are volts per meter. If you compare across these techniques, you can see that they are quite different. They're having quite a party over there. We should change the room. So you may well ask, why are personalized physics models we needed? And when we started doing this, we didn't know really if we actually needed this to this level of detail. We guessed, I think. But there are studies coming out showing what are called dose response curves of the application of the electric field and the effects that you see physiologically, behaviorally. So here's a couple of them. I want to highlight maybe one that comes from our own work, showing that this is a dual task cost reduction from some subjects. And this, in the x-axis, you have the average electric field on the target. And since we use a standard montage for all of them, this resulted in the variability of the average electric field on the target. And we found a nice correlation, as other people have done in other types of work. So we know that we need to model to within a 5% or better, probably, what the electric field is in the targets that we want. We also know from work from others as well that that anatomy has a big impact on the electric field. And actually, the amount of variability that you have, it's more like 20%, just from subject to subject. If you use the same montage, you end up with variances that are about 20 to 25% of the average value. Here's an example of the same montage on two subjects, same currents and everything. And depending on the anatomy and the thickness of the skull, the CSF and so on, you can have quite different electric fields. So the main conclusion is that we do need to model this. And in fact, we also know that if we use techniques for montage optimization, we can actually control the electric fields quite well. So in this plot, you can see that, especially in normal components, we have a much better, much less variance in the actual electric fields that are produced in a set of subjects if we actually optimize and take care of the physics. Okay, so this is now at Neuroelectrics, it's an operational pipeline. So this means that it's kind of an industrialized process by which we get data from hospital, from clinician, T1 data, and we have a process by which we start from the MRI, we create a finite element model, we deploy the electrodes in the model, we compute the electric field, and if you give us a target, which means here a region in the brain that you want to stimulate and what direction you want to stimulate it and how important is this region with respect to others, then we can produce automatically a montage for a subject. The part that is less under control here, I think, and that's why neurotraining is important, is the definition of the target, which right now is called given, or neurologist given, which is kind of the same thing. And that we need to understand better for different pathologies, what should the target be? And we have a model of what the pathology is and a brain model. It's really hard to do that, I think. We have used this physics pipeline with these fixed targets from neurologists in our epilepsy program, and we did already some years ago a pilot study using this personalized brain stimulation technique in medical refractory focal epilepsy, in collaboration with partners in Boston and Mexico. And well, the results we obtained is that this was an open label study, but we obtained a median responder rate of about 47% seizure reduction in the 2-month follow-up period from 2 weeks of daily stimulation. So 10 stimulation sessions of 20 minutes led to this kind of reduction over 2 months. So we can read more about this here, and this is kind of the basis of one of the works that have motivated to push forward the epilepsy program, but adding modeling to it to understand really what the target should be at the network level. These results have been replicated now recently with our colleagues in Marseille, Fabrice Bartolomé. And we have a pivotal trial underway in the US now with 190 patients, in which this is going to be a randomized control trial for approval, basically. Okay. So, good, more or less. So the physiology of neurotwins. So this is what they call tES 3.0, tES 2.0 being the one with the physics. And now we enter the world of galvanic neurotwin in full, I would say. So this is the picture of what we're trying to do here. So going back to the definition of neurotwin, what we're trying to do here is to develop personalized models fit for purpose of brain stimulation, starting from subject data that can include, depending on the pathology, from SEG to PET, MRI, and the MRI for the connectomics, and the MRI for the structural part. And with that, build a model for the patient that we can use to simulate and optimize brain stimulation. This is the basic idea for neurotwin and galvanic as well. course, I'm very excited that we'll hear more about today, about brain modeling from many people, many experts like Gustavo that is here with us. It has a long history, and I think it's really it's a very exciting time to join this crowd now in the search for these brain model solutions. We started ourselves in the HIVE project with Fabrice, Wendy, and Jean-Merle. As part of the project, we tried to model the effects of brain stimulation on a brain model, which was basically a hybrid model already at the time with a very simple connectome, not a realistic one, but with neural mass models attached to different parcels, with a physics model in which the neural masses were embedded. And this allowed us to simulate EEG and to simulate the effects of tES. At the time, we were interested in tES. And actually, this is kind of an Arnold tongue at the whole brain model that we showed there. And we were trying to relate these two results in that show that the peak frequency to adjusting the frequency of stimulation to each patient will be important. So this is where we started basically doing this. Now, I want to go a little bit through the scales of the problem. So we start with the micro scale. At the micro scale, what we're doing in Neurotwin and Galvani also is basically starting from work by Abera et al. To develop compartment models of the effects of brain stimulation. So leaving behind this simple line neuron model that has this lambda E model that I showed before, try to understand better what the effects of the electric field are. And well, we have developed a methodology now to represent for different neuron types from the Blueprint project. This work at Yap, who's also here with us today. I don't have my glasses on, but yeah. Has been doing, and so we can plot in a spherical coordinate system, in a polar coordinate system, the effects of the electric field at the membrane in different compartment regions. And actually, we have been doing spherical harmonic analysis of this to see if there is something interesting going on. And there is some interesting stuff going on beyond the dipole model, but it's mostly a dipole model. So that's something that's that means that we have been doing quite well with the lambda E model, which is good to know. But there are interesting things that we're writing up some stuff that I can tell you about today. But, and we are building a catalog of cells for the different types of cells that we're interested in the neural mass model. So for each type of cell, we can produce this type of plot, the spherical harmonics, and some statistics about the influenceability of different parts of the cell and so on. For the most part, we're going to be focusing on the soma at the time, because that's what we understand is the most important region. There are some interesting ones. So this is another cell from the catalog, which is called L6 inverted. And it's inverted actually, if you compare with the previous picture, and you look at the polarization, you can observe that it changes color, because it responds in the opposite direction to the electric field. So this is kind of something that is interesting to keep in mind when we do our models, that there are cells that are oriented in different ways, and they can be important as well. I'm going to be talking about now neural mass models a little bit, but I want to point out that even though we're working mostly with neural mass models and Neuroelectrics, we have Hopf models, 5 minutes. Okay, 5 models being developed at the UPF, and we're also working with IC models. But for neural mass models, there are now something called next generation neural mass models, and we will be hearing about today, which actually give you fill a conceptual gap between the function of single neuron to populations. Right now, these neural mass models that we use are a bit ad hoc, they're a bit semi-empirical, but there is this new finding that shows that you can actually make rigorous statements about these neural mass models, which are very important to connect with electric fields as well. So I'm very excited about this work with Pau, which is also here, and others, and we will be hearing about it, I think, from Stephen Coombs later. Okay, mesoscale hybrid neural mass models. We, as I mentioned, we have this representation of population that are coupled together to each other using this type of Janssen-Reed, Wilson-Cowan, and Freeman models. What we have been doing is to connect better with measurements, is to embed them. I hope you can see this. Well, we have embedded them in a physical medium. So to try to represent the position of synapses of these models, and from that, understand how they generate currents. and how these currents can be picked up by different recording systems like SEG, for example, or from EEG, etc., etc. And this is work that is in preparation now that Jose has been working on for a while now, and with Borja also for the physics part. So these are the models that we're going to be using, and in particular for Neuro2, we're probably going to be using this kind of two couple population model that can represent fast and slow frequencies in the brain, which I think are going to be important for the Alzheimer's application especially. Once we have these models with the physics, we can also start understanding what the effects of brain stimulation are. So we can apply electric fields, and in this case, I show you Arnold tongues of the response of the two pyramidal cells, which are coupled to each other, but how each one of them responds if you apply an electric field with different frequencies. And you can see that there are some specific frequencies that the cells like to resonate to, and this may be very important for the Alzheimer application, especially, of the tES in general. We can also use them for the representation of epilepsy, and this is part of the Galvani project. We can add some more features to the neuromass models, like KCC2 transport, chlorine problems for the GABA depolarization, and with that kind of model, we can represent the progression of seizures in a quite nice and simple way. So they are quite versatile, these models, I would say. In Neuro2, we're now thinking hard about how to use them to represent the physiopathology of AD, what we know about it. Javier is going to be telling us some more about it, I hope, today. We have been reading some of his work to map the mechanisms that we understand from the literature involved in Alzheimer's disease, from inflammation to the presence of beta amyloid oligomers, failure of the inhibition, fast inhibition, and how this leads to further damage in the brain, but specifically how this relates to electrophysiological findings or PET or fMRI both. So we're trying to connect these two worlds through this modeling approach too. And I think we're on the right track in that sense. Hopefully, by the next meeting, we'll have something more to say. Yeah, and there's been recent work in which we have been involved as well, pointing in the direction that with tES at the right frequency, you may do something about Alzheimer's, very preliminary stuff. But we understand that there is a problem with the fast circuitry in the brain. And with tES, as I showed you, you can actually entrain these fast spiking populations, and through plasticity, the hope and the idea, I think, has been that we can recover some of that function. And some animal work has been pointing out in this direction by people at MIT. Okay. And I guess I wanted to mention here also, yeah, I think that was enough for now. But Javier is going to be telling us more about this. I'm very happy that he's joined us. We have been collaborating with people in Boston, with Emiliano's team there, in a first open label pilot in AD, 40 Hz stimulation. And even though this is a very small pilot, 15 open label patients, there are indications that at the level of brain perfusion and PET, there are some changes in the brain of these subjects. Part of the project in Neuro2 is going to be analyzing this data from tES stimulation for several multi-sessions for several weeks up to a month, and trying to understand if we can see some changes in these brains from the stimulation that can guide us in the development of the protocols. Animal work, we are also doing non-human animal work in the project with people at Pablo Lavide. Javier is with us here today too. So we're developing animal models to study the effects of tES, to try to model AD and see that we can understand better what the mechanisms are and what not. Yeah. Okay, so what do I want to say about microscale? Microscale is going to be discussed a bit further. As I mentioned, we're going to be studying from different scales, including the very simple scale of the Ising model, abstraction level, sorry, it's microscale now. So this is a simple level of abstraction, the Ising model, that can tell us something about the critical features of the brain. And maybe we'll learn something about AD in this sense as well. Gustavo is very interested in modeling the dynamics of networks with models. So that's part of the work in Ruffini as well. And he will be talking about dynamics of brain networks and turbulence today. In Galvani, we're also doing the same, of course, but in this case, we're starting from seizure networks and trying to understand the interaction between seizure networks, between the local networks that are responsible for the problem, to the local seizure network, to the whole brain level, and what that interaction looks like. The idea being at the end of this trip is that when you have the whole brain model, you can start mapping the modeling to the physical world, physical models of and physical measurements of EEG. And you can try to understand what the effects of stimulation are. And if the target is, for example, to recover some electrophysiological aspects as a therapeutic target, then we can actually model this in detail and optimize the stimulation, which is the final goal. So, yes, finally, I want to mention the work at FADO, which has to do also with Michael, which has to do with trying to understand if we can induce and stabilize oscillations in the brain. So we know with tES you can entrain ongoing oscillations, but it's really hard to initiate them. So part of the work that has been done by Michael, actually in the context of the Luminous project, was to show that if you combine tES with TMS, if you start oscillations with TMS and then you phase lock with tES, you can get enhanced results from the stimulation. So this is a technology that could be also very useful if the goal is going to be to increase oscillatory behavior in some bands. And okay, let me skip this. Yeah, this is the summary of the story. So going from tES 1.0, where we started with the initial work that Michael did with sponges, and to the next phase in which we deployed small electrodes and try to do physics models of how to optimize the stimulation, and where we are today, which is trying to create models and optimize stimulation based on models, define targets based on the models as well. So that's my last slide. Yeah, so targeted multi-channel montages using small electrodes offer the opportunity for more precise, meaningful stimulation of single targets or networks. But how do we do that? Well, we have now a physics operational pipeline in place to do this, but we want to actually go to the next stage, which is to do it in a model-driven way. And this is my team, which I would very much like to thank for the great work and enthusiasm that they're putting in the project. And special thanks to Christina today for organizing the event. I know it has been a lot of work. And thanks to my collaborators and many more collaborators that I hope to develop from this project and workshop. Thank you.